linked in some, I don't know, truly bizarre way, even if they're light years apart.
Right.
You measure one, and instantly the other seems to know what happened.
Yeah, it's like they're sharing a secret, a single fate.
Exactly, a single fate across space. So, for you, our listener, if you like getting those quick insights, those aha moments, well, we're diving into quantum entanglement today.
One of the weirdest corners of physics, really.
And the big question, the one that really messes with your head, were the properties of these linked particles decided from the get-go?
And what's cool is the material we're looking at tackles exactly that. It uses this idea of local realism, which feels totally intuitive, but experiments have, well, sort of punched holes in it.
Local realism. Okay, yeah, it sounds technical, but the basic idea feels like common sense, doesn't it?
Totally.
Things have definite properties, like this pen is black, whether I'm looking or not. That's the realism part.
That's realism, yeah. It exists with its properties.
And locality means things can only be affected by their immediate surroundings, right? Nothing travels faster than light to influence something else far away.
Precisely. My actions here don't instantly change something on Mars.
So the classic example, like if I have a pair of gloves, one left, one right, put them in separate boxes and mail one to you.
Okay.
When you open your box and find a left glove, you instantly know I have the right one. But that's not strange, is it? The leftness or rightness was determined from the start.
Exactly. That's local realism in a nutshell.
Yeah.
The property was always there. And finding it out locally didn't change the other one instantly. It was already set.
Okay, so our mission for this deep dive is to figure out why this perfectly reasonable picture just falls apart in the quantum world. Why do the experiments tell us something completely different about entangled particles? This is kind of your shortcut to grasping something fundamental but really strange about reality.
And maybe even how this strangeness could be useful down the line. Things like quantum computing hinge on this stuff.
Right, so let's paint a clearer picture of entanglement itself first. What is it, fundamentally?
Well, as our sources lay out, it's this really deep connection. Two or more particles described by a single shared quantum state.
A shared state.
And the key thing is measurement. If you measure a property like, say, the spin or polarization of one particle, the result is immediately correlated with the measurement of the same property on the other particle. Instantly, no matter how far apart they are.
Instantly. That's the word that always gets me. It feels wrong. Like breaking some cosmic speed limit.
It certainly feels that way. Very counterintuitive. Einstein famously called it spooky action at a distance.
Spooky. Okay, so local realism has those two parts again. Locality and realism. Let's just nail those down.
Okay, so realism, the particles have definite properties before we measure, like our gloves being left or right from the start. They aren't in some fuzzy maybe state.
Got it. Definite values.
And locality influences can't travel faster than light. Measuring one particle can't instantaneously affect the distant one. Any influence needs time to travel.
Okay, makes sense. So applying that common sense to entangled particles, you'd think, okay, maybe they agreed on their properties when they were created.
Right, like they were programmed together.
And that leads straight to this idea of hidden variables, doesn't it?
Exactly. The hidden variable idea was proposed to sort of save local realism. It suggests there are these hidden instructions, properties we just can't see or measure yet, that each particle carries. These instructions predetermine the outcome of any measurement. So the correlation isn't spooky action at a distance, it's just pre-programmed coordination.
Like finding the left glove because it was always the left glove, determined by some hidden glove identity variable.
A perfect analogy, yes. It makes the correlation seem understandable again, within a classical framework.
Sounds much more comfortable. So if that's the intuitive, comfortable explanation, what blew it up? Ah, yes, Bell's theorem. This feels like the moment everything changed.
It absolutely was. John Stuart Bell, back in the 1960s, did something brilliant. He found a way to actually test if any theory based on local hidden variables could possibly explain quantum mechanics.
Oh, how do you test something like hidden instructions?
He derived a mathematical inequality now called Bell's inequality. It basically sets a limit.
A limit on what?
A limit on how strongly correlated the measurements on two separate particles could be, if local realism and hidden variables are the correct explanation.
Okay, so it's like a mathematical speed limit for correlations based on common sense assumptions.
Pretty much, yeah. He assumed local realism was true, however. Particles have definite properties, only local influences. Then he calculated the maximum statistical correlation you could expect under those rules, especially when you measured different properties at different angles.
And quantum mechanics predicted something else.
That's the kicker. quantum mechanics, because it describes particles in this indefinite superposition, they don't have a fixed property. Until measured it predicts stronger correlations than Bell's limit allows.
Stronger.
Because they're linked in that single quantum state, they can coordinate in ways that independent particles with preset instructions just can't. Quantum mechanics predicted that if you did the right experiments, you'd actually violate Bell's inequality.
Wow. So a direct clash. Either Bell's inequality holds and local realism wins.
Or it's violated and quantum mechanics is right, meaning local realism as we understand it must be wrong.
Which brings us to the experiments. Elaine Aspect's work is famous here, right?
Groundbreaking work in the early 80s, yes. And many, many experiments since then have confirmed and refined it.
So what did they actually do? How do you test this?
The basic setup is you create pairs of entangled particles. Photons are commonly used.
Light particles.
You send them in opposite directions towards detectors. Crucially, these detectors are far apart.
Far enough so light couldn't travel between them during the measurement.
Exactly. To rule out any sneaky light-speed communication influencing the results, that tackles the locality loophole.
Makes sense. And the measurements themselves.
They measure properties like polarization. And this is key. The settings of the detectors, like the angle they measure polarization at, are changed very rapidly and randomly.
Randomly? Why random?
To close another potential loophole, it ensures the particles or detectors couldn't have, agreed beforehand on how they'll respond based on the settings. The choice of what to measure is made too late for any hidden signal to coordinate things.
Super fast, super random measurements on lots and lots of entangled pairs. Then you crunch the numbers.
You crunch the numbers. You look at the statistics of the correlations between the results of the two detectors.
Then drum roll.
The results were stunningly consistent. Experiment after experiment, with increasing precision, showed a clear violation of Bell's inequality.
So the correlations were stronger than local realism allows.
Significantly stronger, and they match the predictions of quantum mechanics almost perfectly.
Wow. Okay, so goodbye, local realism. Or at least one part of it.
Well, that's the profound implication. If Bell's inequality is violated, at least one of the core assumptions underpinning it must be false.
The assumptions being realism and locality.
Exactly. So either realism is false particles don't have definite pre-existing properties before measurement. The measurement itself kind of defines the property. Or locality is false. Measuring one particle can somehow instantaneously influence the other, no matter the distance. That's what we sometimes call quantum non-locality.
That spooky action at a distance.
As a spooky action, yes.
So which one do physicists tend to think is wrong? Realism or locality? Is there a consensus?
It's still debated, and different interpretations of quantum mechanics handle it differently. But I'd say the majority lean towards giving up realism in the classical sense.
Meaning properties aren't fixed until measured.
Meaning properties like spin or polarization emerge, in a way, from the interaction of measurement. The particle existed in a superposition of possibilities, and the measurement forces a choice. It wasn't hiding a predetermined answer all along.
So the entangled particles weren't carrying secret instructions. The correlation isn't because they agreed beforehand.
That appears to be the case. The strong correlations, the ones violating Bell's inequality, can't be explained by preset instructions within each particle.
Where does the information for the correlation come from, then?
It seems to reside in the shared, non-local quantum state of the entire system, the entangled pair as a whole, rather than being parceled out to individual particles before you look.
Okay. So our basic intuition about how the world works, definite properties, local influences, it just breaks down at this fundamental level.
It really seems to. It's a profound challenge to our classical worldview.
It really is. The implications are just huge, aren't they?
Absolutely. It forces us to rethink fundamental concepts about reality, information, space, and time.
So let me leave you, the listener, with this thought. If these properties aren't predetermined, what does that actually mean about reality?
Right. Does measurement create the outcome? Does it define what's real at that moment?
And what about this non-local connection? If it's real, how does it work without violating other physical laws, like the speed of light limit for information transfer? It seems like it should, but the maths, well, it works out somehow.
It does. It's a subtle point. You can't use entanglement to send faster than light messages, even with the non-local correlations. But the connection itself seems instantaneous.
It really just opens up more questions, doesn't it? This dive into entanglement kind of throws you into an even deeper, stranger ocean.
Definitely. challenging our assumptions, pushing the boundaries of what we think we know. It's what makes this area of physics so incredibly fascinating. And there's still so much more to explore and understand, perhaps in future dives.
Indeed. Lots to think about there.